Okay, so welcome everybody. So now we continue with our second lecture of Xenia Drimika Polu. I think I did it all right.
Really did, yeah.
Who will continue with the second lecture on Introduction to Grand-Prasad conjectures or conjecture. Okay.
Thank you. So yeah, we're just going to pick up from where we left off last week. So the first part of today will be some basics on automorphic forms. I'll define automorphic forms and automorphic representations, and all maybe the small little definitions that we need to move on to the statement of the Gann-Prasad conjectures. Time allowing, we might also talk about a refinement of the conjectures. If not, that will be pushed on to later this week on Thursday. All right. So let's begin. Is the size okay, Luis, at the back? Okay. Okay, so let's consider F a number field. And we will denote by FV the local completions. At the places V of F, as usual. Now, I will define the automorphic forms and automorphic representations for general linear algebraic groups. The conjectures are for more specific ones, but it doesn't do any harm to do this in bigger generality. So let's consider G a linear algebraic group. Which we will need it to be connected and reductive. And maybe I should change. Oh. Yeah. This is better. Okay. Cool. So, fixing a faithful representation. Algebraic representation. Rho of G inside GLN for some n. We obtain a system of open compact subgroups of G by considering the pre-image from GLN into G. We will denote these subgroups by KV, and they will be just rho minus 1 of GLN of OV, where OV is just the ring of integers in FV. And now, you've probably all seen this before, but we define G of the Adels to be the restricted product of G of FV, where it's a restricted product with the restricted product is with respect to the system KV. Great. As before, and maybe I will put this in a little box up here, which is where I can't really reach, so it's going to be things that I won't really be erasing. I think, so we will denote by brackets G of the Adels of F, mod G of F. Last time we also considered it to have the center, I think maybe, but this time we'll just say it like that. This is the automorphic quotient, and note that G of the Adels acts on the automorphic quotient. I did not write that this is the, oh, okay. This is hard to write up there, but that's what it's called, the automorphic quotient. So I'll just write it here. The automorphic quotient.
There should be AF again.
Yes, thank you. Because we fixed F, if I forget it again, just think that it's AF. So this acts by right translation. Great. So now we can define automorphic forms. So an automorphic form F on G is a function F from the automorphic quotient to C such that it satisfies a bunch of conditions. So last time we saw these conditions more specifically for GL2, but they're going to be the exact same ones here. So the first is that F is smooth. Then we also need that F, sorry, I got distracted. F is right KF finite, where KF is the product of these KVs at all places without the Archimedean component. And we also need this mysterious condition that we had last time, that F is of moderate uniform growth. And finally, as last time, F is ZG finite, where I can never really draw the curly G, but this should be some curly G, and it's the Lie algebra of G. Maybe I'll just make it a different color because I can't really write curly. Great. So to ease notation, we denote the space of automorphic forms on G by AG. And again, note, and this should be quite straightforward, that G of the Adels acts on A of G, again by right translation. All right. Any questions?
Oh, just observation.
Yeah.
Smooth is something at infinity, no?
Sorry?
The first condition is at infinity.
Yes.
And the ZG is enveloping algebra.
Yes. But I'm just avoiding explaining exactly what this means because it's very definition heavy. But all these things are quite standard, so you can find them more explicitly. The thing is that it doesn't hurt to think of these conditions as how we saw them last time for GL2. That intuition should be enough to help you understand what kind of functions we like using. All right, so since G of the Adels acts on the space of automorphic forms by right translation, this makes AG a GA module. Right, so this allows us to move forward and have a second definition, which is that of automorphic representations. So, an automorphic representation on G is an irreducible subquotient of the G of the Adels module AG. Oops. If pi is such an irreducible representation of G of the Adels, then pi is a restricted tensor product of pi v, where v are all the local the places, sorry. Right. Cool. Any questions?
By this representation of GFP.
You said yes. Thank you. Great. And finally, we have a subspace of A of G of the automorphic forms, which are called cuspidal automorphic forms, following the same ideas of modular forms. So, a cuspidal form of G is an automorphic form such that the integral, maybe I should define this for later, which we will denote by f and g, which is just the integral over the unipotent radical of f and g dn is 0. Is there a question? Okay, and we denote such cuspidal automorphic forms by A0 of G, which is a subspace of A of G. Great. Now, the following fact is not easy to prove, so I will just state it, but what's interesting is that we can decompose this A0 of G as a direct sum of MP P, where MP is of finite multiplicity. And an irreducible summand of this space here is what we called maybe I'll write it up there. It's called a cuspidal automorphic representation, as you probably all expect. It's the unipotent radical of G. I'll write it. So it's called a cuspidal automorphic representation. And n is the unipotent radical of G. Any other questions?
So maybe this n is not the unipotent radical of each Borel of G.
Yes, you're right.
So
I need to be a little bit more careful.
For each Borel, you need a condition, something like
Yes.
that. Or...
So how do we define n? For each parabolic P, which decomposes as m times n, we have the condition star, which star is this condition here. Okay, thank you for that. That is actually very important. Anything else? Okay, very good. So we do have more definitions, I'm sorry, but the pain will end soon, I promise. So now fix a subgroup H of G. Right. We can define, as we did last week, the automorphic period integral, which is a function, pi h, from the cuspidal automorphic forms to C. And how do we define it? We take such a form and we send it to H mod by ZG of the Adels phi H dH. Right, so we saw exactly the same situation on Thursday, but just for GL2, and things are really nicely behaved in the sense that the definitions extend in a very natural way. So,
there, as Ariel mentioned last time, there is something with the center, no? Maybe?
yeah, so I don't think so.
No?
I looked into it and
Yeah.
I don't think so, but we should discuss this later.
Yeah, some people put 1 over the group, you remember? So no, but it's okay, just...
You can define this with twists with characters.
Yeah.
But I don't think to define this you need a unitary central character.
Excuse me?
Yes.
What was n? What was the radical?
So n, so you take a parabolic P of our group G, you decompose it as m times n, and that's the n that appears here. Great. And when I write n or h, I always mean the same thing as I wrote up there. The automorphic quotient stays the same. Right. So as I because I just mentioned it to Daniel, I'll just write it. If chi is a character, so if chi is a character of the automorphic quotient left quotiented by the center, then we can define the twisted automorphic period integral as what you would expect, I guess, or what I've said already, is just phi of h, and then you times it by chi h dh. Right. we won't see this again, but since I mentioned it, I thought it makes sense to write it down. Okay, any questions before I delete this? Cool. It's all quite standard. Hopefully you, even though it's very, very definition heavy, if you haven't seen this before, again, just keep in mind what happened last time, and everything extends quite naturally.
More about you didn't have actually a restriction because we were questioned by the restriction of scalar and then another function. And that wasn't a subgroup of GL2.
Okay.
So I think that's why she needed the trivial.
Maybe. Okay,
But in this case, if you have this as subgroup,
okay. Thank you. Right, and our final definition, and we're doing very well on time, is the following. Oops. A cuspidal automorphic representation pi of G is globally distinguished by H if we consider now the restriction of the automorphic period integral to pi, here, if we just consider the irreducible sum of pi in here, which is just going to be an element of the home space pi, comma, C. If this pi h, pi is non-zero, that means that there exists some element of pi such that when I evaluate at that, the integral doesn't vanish. All right. If pi is globally distinguished by H, then we have that. The same condition holds, but instead of looking at the whole adels, we just look at each completion every time. I'll just write it down. For every place V, we have that the home space H, phi V, C is non-zero. And we say in each of these specific cases that pi V is locally distinguished by H. All right. So we're done with our definition heavy section. So as we saw last time, the automorphic period integral appears. And what we're trying to do here is link automorphic periods like that with certain L values. And when we study these things, practically what we were doing last time, we wanted to link this is non-zero if and only if something else, an L value, is non-zero. So seeing where this vanish is equivalent to seeing when this home space here is non-zero, as we saw last time. Sorry, I think what I just said was wrong. When that vanishes, identically, this home space is identically zero. It's just zero dimensional. And when it doesn't vanish, this is a bigger space. It has a positive dimension. So the question now is, when do these automorphic period integrals behave nicely? Because last time we were talking about the GL2 case, H was the torus, and we knew that we could have some specific results there, initially by the work of Hecke, and eventually by the work of Valls-Pouget for more general tori in our GL2. But the situation is very, very interesting, actually, for a more general class of groups. So the question now becomes, when does pi h behave nicely in some sort of way? By nicely, I mean, when do we want to study these things? Another way to reformulate this is, when do we have that the dimension of the home space H, F, V, pi V, C is less than or equal to 1? And when we have results like that, this is just for general culture, maybe not necessarily needed for to the statement of the conjectures. This is called a multiplicity-free result. So if we have a situation like this, where the dimension of the home space is either 0 or 1, then maybe we can start linking, okay, the dimension is 0, the L function vanishes, the dimension is exactly 1, then we have a specific formula like we did last time, where this thing, for specifically nice groups G and H, can be linked to L values, yes. Left. So we start caring about these automorphic period integrals. We want to know when they behave nicely in some sort of way. For us, nice is going to mean, when does the dimension of these local home spaces is multiplicity free, i.e. it's either 0 or it's 1. And the answer, well, the expected answer is that we expect, of course, that this is the case for a class of pairs GH known as spherical pairs. So again, this is not really necessary for the conjectures, but I think that at this point it's actually quite interesting to talk about spherical pairs for just maybe a minute. So let's define what these are, and then maybe give some examples. So we usually write HG, so I just want to be consistent. So for a group G and the subgroup H of G, we call the pair HG spherical if a Borel B of G has an open and dense orbit, excuse me, in G mod H. All right, so this might be a little bit of a weird definition if you've never considered quotients like that. But it turns out that it's very, very useful. And if you want to know why these are useful in a more general setting, or maybe a different setting, come to my talk next week. But let's give some examples so that people that have never seen these before can start thinking about what these spherical pairs look like. The first example is that if we take G, a group, and then the product of two groups, where we see G diagonally embedded in G times G. Right, so for a group G and a subgroup of it H, we call the pair H comma G spherical if a Borel B of our group G has an open and dense orbit in the quotient G mod H. And I was just about to give some examples. So a very standard one is you take a group G, and then you take G times G, and you look at G as a subgroup of this via the diagonal embedding, then this is a spherical pair. And my notes are here, yep. Another example is the Whittaker pair, N comma G, where G is quasi-split, and is a maximal nilpotent subgroup. Right, then the third example is known as the Rankin-Selberg example, and it's GLN minus 1, diagonally embedded in the pair GLN minus 1 times GLN, where here you view it, the map here is just G comma G1. This is the map that allows this embedding. All right, and finally, we have what are known as the GGP pairs, which will appear in our conjectures. And these are UN minus 1 diagonally inside UN minus 1 times UN, and SON minus 1 in SON minus 1 times SON. The unitary and the orthogonal cases of the GGP conjectures. All right, so hopefully this was a bit of intuition about why we're going to end up considering specific pairs like that, which end up generalizing Valls-Pouget's result. So are there any questions? Okay, great. So then I'm going to move on to state the conjectures finally. And again, it's going to take a little bit of notation to set up the, we're gonna have to set up some notation, but it should be quick. I don't have a watch. I don't know why I did that. Okay, yeah, I think I can be done on time today. It's better if, I don't know. Anyway, okay. So finally, I will write the whole GGP names down. So a little bit of a historical remark on these conjectures. So Gross and Prasad in the 90s put up a series of conjectures that were mainly focusing on the special orthogonal case. And then with joint work with Gann, they added the unitary case. Now, these conjectures are quite elaborate. And in the paper where they released it, the paper is like 80 pages. So for me to do this in half an hour, I'm not going to state all the conjectures very, very precisely. It's actually quite involved, and I don't think I have intuition about what exactly is supposed to be going on in the more general case. But we're going to do a mini toy, like simple way of looking at the global conjecture. Right, so recall that F was a number field. And now we will just define the conjectures for both cases simultaneously. So on one side, we have what is called the Hermitian case. And on the other side, we have the orthogonal case. All right, so in the Hermitian case, we will take F prime over F to be a quadratic extension of number fields. Quadratic extension. In the orthogonal case, F prime will just be equal to F. Right. Wn will be a Hermitian space of f prime dimension n, and in the orthogonal case, Wn will be a degenerate, a non-degenerate. Wait. A non-degenerate orthogonal space, again with f prime dimension n. All right, and in both cases now we will consider Wn minus 1 to be inside Wn, a non-degenerate subspace of Wn of codimension 1. Right, hence the n minus 1 that appears here. All right, and okay, this is the same for both, but then again here we have a little bit of a division, because here we define Gi to be the unitary group of Wi for I n minus 1 and n, and here Gi, as you probably expect, is going to be SO Wi, again for I n minus 1, comma n. All right, and now we know exactly what pairs we're going to consider, but let's define them. In general, we will take G to be Gn minus 1 times Gn, and then we will take H to be Gn minus 1 diagonally embedded into G. And as we said before, Hg is spherical. I'm using that word a lot so that people start caring about it, but I haven't given you enough intuition, so maybe it's not working. All right. So, are there any questions? Does anybody need, I know there's a lot of buzzwords there, so if someone needs an explanation for some.
What we care about is that the local part is not. I mean, what are we using? What is so special or spherical?
The definition was a bit weird, but the reason I presented it was because what we cared about was the automorphic period integrals. We wanted them to be multiplicity free. What does that mean? That means that when I take my representation pi of v, I restrict it to the subgroup H. I want this to be either the dimension of the home space, i.e. the trivial representation inside of this restriction, either appears once or no times at all. And it's expected that this happens for spherical pairs in general, but it definitely happens for these spherical pairs. So given that we know that these spherical pairs behave nicely and the automorphic period integrals for those are what they should be to generalize Valls-Pouget's result, we can now proceed to see how the conjectures extend. All right.
Excuse me?
Yes.
The conjectures that those.
You'll see the conjecture. Don't worry. I'll write it down. Okay. So, we have time. So, I'll make the conjecture a little bit more precise than I thought I could, which is good. All right, so in the conjecture, central L values of central L values of L functions which look like this appear. Pi will be a capital automorphic representation of G. But now the question is, what is R? And R is a finite dimensional representation of the L group of G. And we can explicitly describe this L function as a Rankin-Selberg convolution of suitable representations of GLN. So pi will be pi n minus 1 tensored pi n, because the n minus 1 will mean that it's a representation of this component, and pi n meaning that we consider a representation of this component. All right, so we will get that ls pi r is going to be equal to ls, and now here we'll have a big pi n minus 1 f prime tensored, times is probably n f prime. So now in each of these cases we can explicitly describe what these are. This now. All right, so for each I, this pi I f prime will be some endoscopic functoriality. So some endoscopic factorial lift. From, oops. From, well, sorry, I just deleted it for a reason, of pi I from GI to GLN for some n. So in the Hermitian case, we do base change from GI to GLN, sorry, GLI, where I is either n minus 1 or n. Okay. In the orthogonal case, we have two cases. So we do endoscopic transfer from GI to GLI if I is even, and from GI to GLI minus 1 if I is odd. And I know this is very, very definition heavy, and I haven't defined what all these things are, but it's quite involved. So the only intuition that you should care about here is that we start with a representation of this group here. We attach a specific L function to it. The L function in this case is, it only depends on our representation pi, and it turns out that it's just a transfer. You can transfer this to a more general setting. I map this representation pi to a representation which is of the general linear group, and then just take the Rankin-Selberg convolution L function. All right, so if all this means nothing, just think that this is the correct L function that we need to care about. and leave it at that. You're probably not missing out too much by not knowing the exact definitions of all these things, because even if you do, it's so definition heavy that getting intuition about why this is the correct function is not something I can help you with. So if I'm being completely honest. But if you just think about the case that we began with, then all this is just a natural extension of that setting.
So the big pies,
Mm-hmm.
representation of GR.
Oh, I didn't write this properly. You're right. Yes. So we base change this to this, and pi I goes to big pi I, and here is the same. All right. And now we can state the conjecture, so that's great. Right, so conjecture. So consider let pi be pi n minus 1 times pi n be a tempered cuspidal automorphic representation of G. Then the following are equivalent. Firstly, there exists some phi in pi such that the automorphic period integral doesn't vanish. And secondly, as we had last time, the central L value of this L function that we care about is non-zero, and we have that pi v is locally distinguished at every place. Right. That's it. That's the statement of the conjecture. Are there any questions?
About this representation, should be one, is a specific one, or for example, there.
Sorry, which one?
So in the other side of the board, you say R is a finite dimensional representation of L group of G.
Yes,
This should be a specific one, or
it's a specific one. Yes, it's chosen.
because in the left or right, okay, in the right hand side.
Sure, but
One can think is like a standard representation of G and that function.
okay, think of this L function as
Does this?
So R in the conjecture is the same.
Yes,
Yes,
the same
the
way
same way
G
G
is the
is.
same as before on the board, un minus 1 times un, or son minus 1 times son. All right. So any more questions about the statement of the conjecture? Okay, so I'll give you some remarks.
Maybe I'm confused, but
Yes.
can we say that this try to solve the question if the automorphic representation is globally age distinguished, if and only if locally is not true, but you need to add the cell value condition. That is what it's saying here.
But it's what you asked before that I
Yeah.
didn't really know the answer to. So,
Huh?
like this global local distinguishability that I thought was one thing, but apparently might not be.
No, it's exactly that. No, in the second point, is
Yes.
locally H distinguish for each V plus L values is equivalent to globally H distinguish. No. Yeah.
Yes. Yes, you're right. Yeah. Right. So last time the conjecture, the result was this, but then we had a more explicit formula for it. We could write explicitly the automorphic period integral equal to a bunch of L values. And that's called the Ichino-Ikeda refinement. And I'll write that down now since we're good on time, actually.
Here we are always good.
All right, so this is just going to be a very long formula that I'm just going to write down so that people have seen it, but don't worry too much about understanding every single component of it. I'll just write it down and then I'll explain each factor. It's not going to fit here, but it's fine. Yeah, I'll definitely be done in 10 minutes. And then this whole thing is times something else that doesn't fit there, so I'm gonna write it here. All right, so what is this long formula? We have the automorphic period integral squared as we had last time. This is exactly as last time. And then we have some factor here where veta is an integer related to the L packet of G, the size of some near equivalence class, it doesn't really matter. Eta is the quadratic character. Associated with f prime f. The adjoint L functions are as we defined them last time. Is there anything else? Oh yeah, and S is a sufficiently large set of places of of F. So R was some finite dimensional representation of the L group, which I didn't define because it's a specific one. But you can just think of this as the Rankin-Selberg convolution of some other representation pi of a Rankin-Selberg product, where you can transfer this small pi to those big pi's with a very explicit recipe. Okay, anything else? Oh, these alpha v's are, as last time, some correction factors. at the bad primes. At the bad places.
This formula is for the conjectures.
Yes.
Yes.
It is quadratic.
This specific one,
And it is for the unitary case.
You have a quadratic.
Yes, yes. You're right. Anything else? Cool. And I'll just give you some remarks about the statement, the progress on the conjectures. All right. So, firstly, remarks. Sakelaridis and Venkatesh showed that the alpha v's don't vanish if and only if the representation is locally distinguished by H. And we had something very, very similar last time. Secondly, there is a very explicit recipe which describes when home HV, IV, C is non-zero, only using root numbers. And thirdly, the main remark is that the unitary case, the Chino-Ikeda refinement of the conjecture and the conjectures, they're a theorem now. So, due to the works of, and now this is going to be a big list of names that won't include everyone. So, due to the works of Beaux-Arts-Plessis, Yun, Zhu, Zhang, and others, the unitary GGP conjecture is a theorem. And due to, again, Beaux-Arts-Plessis, Chaudouard, I don't really know how to pronounce his name, and Zidore, the Chino-Ikeda refinement is also a theorem. And as for the orthogonal case, they have it's been proved up until n is equal to 3 in full generality, I think, for like general temporary representations, and up to n is equal to 5 with some specific conditions, but I'm not entirely sure what the conditions are. So I'm not gonna write that down because I'm not entirely sure. But yeah, that's it for today.
So, there are any questions? Maybe here, no? Maybe on Zoom? Actually, maybe I have a question. So, the refinement implies the non-refined version?
yes.
Or maybe you need the secondary computation for it? Or
Yes, so the refinement of the conjectures like this by itself implies it because this is non-zero if and only if this doesn't vanish and this doesn't vanish, right?
Ah, yeah.
And then this condition here is linked to the local distinguishability, and the second one with the vanishing of the L function stays the same. Just as a quick
to what happened last time. When we had a formula like that in the Hecke case, in the very standard torus inside GL2, this we knew that didn't vanish, so we were fine. And then when we refined it and we took a more general torus, this was a little bit more involved because it could vanish identically, so we needed some more conditions. And that stays the case now in the more general setting. Yeah.
So no more question, I guess. Okay, so let's thank the speaker again. Roseni. Okay, thank you for everybody. So see you on Thursday, yes? Maybe.
Yes.
Yeah.
Yes?
Yeah, definitely.
It was Thursday, yes. Bye. Ciao,
Ciao.
ciao.